On a cold April morning in 1911, in a laboratory in Leiden, the Netherlands, a quiet revolution in physics was underway. Heike Kamerlingh-Onnes, a Dutch physicist fascinated by the mysteries of low temperatures, had just achieved what many thought impossible. Only a few years earlier, he had succeeded in liquefying helium, reaching temperatures just a few degrees above absolute zero. This triumph unlocked a new realm for scientific exploration, a stage where the strangest behaviors of matter could be revealed. That day, as his team cooled a slender wire of pure mercury below 4.2 Kelvin, colder than any naturally occurring environment on Earth, they watched the resistance in their circuit plummet, not gradually as in ordinary metals, but in a sudden, precipitous drop. The resistance vanished entirely. No matter how precise their instruments, they registered no opposition to the flow of electrical current. For the first time, humanity had witnessed the phenomenon that would become known as superconductivity. The discovery of superconductivity was not a mere curiosity. It posed a profound challenge to the established laws of physics. Until that point, it was well understood that metals conducted electricity and that their resistance to the flow of electrons decreased as they were cooled. This effect, observed in materials like platinum and gold, was predictable and continuous. But what Kamerlingh-Onnes and his co-workers found in mercury was something utterly different, a complete and abrupt disappearance of resistance at a sharply defined temperature. This temperature, now known as the critical temperature, or T sub C, became the defining boundary between the ordinary and the extraordinary. Kamerlingh-Onnes was meticulous in verifying his results. He devised experiments using loops of mercury wire and observed that, once set in motion, an electrical current would persist indefinitely. With no resistance to impede them, the electrons in the circuit would circle endlessly, needing no further push, as if the very fabric of the metal had become a frictionless road. For these fleeting moments in the frozen laboratory, it was as if the rules had changed and energy could flow without loss. This property zero electrical resistance is the most immediately striking feature of superconductors. In the everyday world, all conductors, from the copper and household wiring to the gold and delicate electronics, possess some resistance. Resistance causes wires to heat up and energy to dissipate as current flows. It is a constant adversary for engineers, a barrier to efficiency. But when a material becomes superconducting, that barrier vanishes. The electrons glide through the lattice unimpeded, and energy loss drops to zero. A current, once established, can flow forever, at least in theory, and within the limitations set by the material and its conditions. Yet as spectacular as zero resistance is, it is only half the story. In 1933, over 2 decades after the Leiden discovery, Walther Meissner and Robert Oxenfeld made another remarkable observation. When they cooled a superconductor, this time a piece of tin below its critical temperature in the presence of a magnetic field, the material did not just allow the field to pass through, nor did it simply ignore it. Instead, the superconductor expelled the magnetic field from its interior. This expulsion was complete and active, not merely a consequence of perfect conductivity. The phenomenon, now known as the Meissner effect, became a defining hallmark of the superconducting state. It sets superconductors apart not only from conventional conductors but also from the perfect conductors imagined in earlier theories. The Meissner effect is more than a laboratory oddity. It is the reason why superconductors can levitate magnets, a phenomenon that seems to defy gravity and intuition. When a magnet is placed above a superconducting material cooled below its critical temperature, the superconductor develops currents on its surface that generate a magnetic field exactly opposing the field of the magnet. The result is a delicate balance. The magnet floats above the superconductor, held aloft by invisible lines of force. This perfect diamagnetism, as physicists call it, is unique to superconductors. No material in the ordinary world shares this property. At the heart of superconductivity, then, are 2 remarkable properties: zero electrical resistance and the expulsion of magnetic fields through the Meissner effect. Together, these define a phase of matter as distinct from ordinary metals as ice is from water. But what is it, at a fundamental level, that enables these properties to emerge? Why does cooling a piece of mercury or tin to a critical temperature unlock such radically new behavior? For nearly half a century after Kamerlingh-Onnes' discovery, the answer remained elusive. The phenomenon seemed to defy explanation by the classical physics of the day. Ordinary conductors lose resistance as temperature falls because thermal vibrations of the atoms decrease, giving electrons a cleaner path. But even the purest metals always retain some resistance at the lowest temperatures due to defects or impurities. Superconductors, however, behave differently. Their resistance does not merely approach zero, it vanishes abruptly, as if some hidden switch has been thrown. The breakthrough in understanding came in 1957 with the development of what is now called the BCS theory, named after John Bardeen, Leon Cooper, and Robert Schrieffer. According to this theory, which draws on the strange rules of quantum mechanics, electrons in a superconductor do not move independently. Instead, under the right conditions, they form paired states, now known as Cooper pairs, that can move collectively through the atomic lattice without scattering. In this paired state, the electrons act as if they are a single quantum entity, immune to the usual sources of resistance. The formation of these pairs is triggered when the material is cooled below its critical temperature, and it is this quantum dance that gives rise to superconductivity. Yet not all superconductors are created equal. The first materials to display this behavior, like mercury, tin, and lead, are known as Type I superconductors. These are typically pure metals with relatively low critical temperatures, only a few degrees above absolute zero. Type I superconductors exhibit a complete Meissner effect, expelling all magnetic fields from their interior as they enter the superconducting state. However, they are limited in practical applications, since they cannot sustain superconductivity in the presence of strong magnetic fields. Later discoveries revealed another class, the Type II superconductors, which are often alloys or compounds. These materials can withstand much higher magnetic fields before losing their superconductivity, making them especially valuable for applications requiring powerful magnets, such as those found in medical imaging or particle accelerators. The underlying physics of Type II superconductors is more complex, and their behavior in magnetic fields is characterized by the formation of vortices, tiny tubes through which magnetic flux can penetrate, surrounded by regions where superconductivity persists. The distinction between conductors and superconductors is thus not just a matter of degree, but of kind. In a conventional conductor, electrons are scattered by the vibrating atoms and imperfections in the material. This scattering is the source of resistance, a process that wastes energy as heat. Cooling the material reduces the vibrations and the resistance drops, but it never reaches zero. In a superconductor, something more profound occurs. The electrons undergo a collective transformation, entering a state where they move in lockstep, immune to individual disturbances. Resistance is not merely reduced, it is abolished. The Meissner effect further emphasizes this difference. A perfect conductor, in theory, would allow magnetic fields to persist within it indefinitely, merely freezing them in place as the temperature drops. A superconductor, by contrast, actively expels magnetic fields as it transitions into the superconducting state. The magnetic field is pushed out, a process governed by the fundamental equations of electromagnetism and quantum mechanics. This behavior is described mathematically by the London equations, which also introduced the concept of the London penetration depth, the distance over which magnetic fields can penetrate into the surface of a superconductor before being expelled entirely. Superconductivity, then, is not a mere extension of ordinary conductivity. It represents a new phase of matter, governed by quantum laws that have no analog in the classical world. Its discovery in 1911 opened a new chapter in physics, one that continues to unfold. Even today, the quest to find materials that become superconducting at higher and more practical temperatures is a major focus of research. The phenomenon has already found its way into technologies ranging from magnetic resonance imaging to the powerful magnets used in scientific research, and it holds promise for revolutionizing how we transmit and store electrical energy. To appreciate the significance of superconductivity, imagine a world where electrical resistance is no longer an obstacle. In such a world, power grids could transmit electricity across vast distances with perfect efficiency. Trains could float above their tracks on cushions of magnetic force, free from friction. Computers and sensors could operate with unparalleled speed and sensitivity. While many of these applications remain goals for the future, the physical principles that make them possible are demonstrated every time a superconductor is cooled below its critical temperature and a current is set in motion, forever persistent, unimpeded, and untouched by the wasteful hand of resistance. Despite over a century of study, superconductivity continues to surprise and challenge our understanding. The BCS theory explained the underlying mechanism for many materials, but high-temperature superconductors and complex compounds discovered in more recent decades defy simple explanation. The basic requirements, however, remain the same. To achieve superconductivity, a material must be cooled below its unique critical temperature, and it must enter the special quantum state that allows for the formation of Cooper pairs and the expulsion of magnetic fields. In summary, superconductivity is a set of astonishing properties that emerge in certain materials at low temperatures: zero electrical resistance and the Meissner effect, the complete expulsion of magnetic fields. These properties set superconductors apart from all ordinary conductors, revealing a world where the familiar rules are rewritten. What began as a curious result in a chilled laboratory has grown into a rich field of study, connecting the deepest principles of quantum mechanics to the promise of transformative technology. As we peer deeper into the quantum world, the foundations of superconductivity remind us that nature still holds surprises, waiting in the cold for those who dare to look. Superconductors, as we now understand them, are not a single, uniform class of materials. Instead, they span a diverse landscape, with each type displaying its own unique relationship with magnetic fields, electrical current, and the subtle quantum processes within their atomic lattices. To navigate this landscape, physicists have developed a classification system based on how those materials interact with magnetic fields. This gives us two principal categories, Type 1 and Type 2 superconductors. The distinction is more than academic. It shapes how these materials are used, their resilience under real-world conditions, and the underlying physics that enables their remarkable properties. Imagine a superconductor exposed to an external magnetic field. For Type 1 superconductors, there is a single decisive boundary, a critical magnetic field strength. Below this threshold, the superconductor remains in its quantum state, perfectly expelling magnetic flux. But once the field surpasses this critical point, superconductivity vanishes abruptly and the material reverts to its normal, resistive state. This sharp transition is a hallmark of Type 1 behavior. The process is binary. Either the material is superconducting and expelling all magnetic fields, or it is not. Type 2 superconductors, by contrast, inhabit a more complex world. When exposed to an increasing magnetic field, they pass through two distinct critical points. Below the lower critical field, they also expel all magnetic flux. But between the lower and upper critical fields lies a fascinating mixed state. In this regime, the magnetic field penetrates the material in quantized threads or vortices, each carrying a discrete quantum of magnetic flux. These vortices are surrounded by regions where superconductivity persists, creating a patchwork landscape within the material itself. Only when the upper critical field is exceeded does the material fully revert to its normal state. This mixed state and the ability to endure much higher magnetic fields make Type 2 superconductors invaluable for technological applications that require powerful, stable magnets. The differences between these types are rooted in their material properties and quantum structure. Type 1 superconductors are typically made from pure elemental metals. They have relatively low critical temperatures and are highly sensitive to impurities or structural imperfections. Type 2 superconductors, in contrast, are usually alloys or complex compounds. Their structure allows for the formation of magnetic vortices, enabling the mixed state and supporting superconductivity at higher fields and, in some cases, higher temperatures. The practical implications are profound. Type 2 materials can carry larger currents and withstand stronger magnetic environments, making them the backbone of technologies ranging from medical imaging to particle accelerators. Underlying all this complexity is the question of mechanism. What precisely enables electrons within these materials to move without resistance? For many years, this question lingered without a satisfying answer. It was not until the development of the Bardian-Cooper-Schrieffer theory, or BCS, theory in 1957 that a microscopic understanding began to crystallize for conventional superconductors. At its heart, BCS theory is a story about electron pairs known as Cooper pairs and their collective dance through the atomic lattice. In ordinary conductors, electrons are scattered incessantly by the vibrations of atoms and by imperfections, leading to resistance and energy loss, BCS. Theory proposes that, under the right conditions, electrons near the Fermi energy, the highest occupied energy level at absolute zero, can interact with the vibrations of the lattice in such a way that they form pairs. These pairs are not bound by simple electromagnetic attraction. Rather, it is a subtle quantum mechanical effect that allows two electrons, each with opposite spin and momentum, to become correlated over relatively long distances within the material. Once formed, these Cooper pairs condense into a single macroscopic quantum state. In this state, the pairs move in concert, immune to the usual scattering processes that plague single electrons. This collective behavior gives rise to the defining features of superconductivity, the loss of electrical resistance and the expulsion of magnetic fields. The Bardian-Cooper-Schrieffer framework predicts several key properties observed experimentally, such as the existence of an energy gap, an interval of forbidden energies that separates the superconducting state from excited states. This gap is directly linked to the stability of the Cooper pairs and the material's ability to resist disturbances from heat or magnetic fields. Bardeen-Cooper-Schrieffer theory also explains phenomena like the isotope effect, where the critical temperature of a superconductor depends on the mass of the atoms making up its lattice. This effect arises because the lattice vibrations, or phonons, mediate the attractive interaction that allows Cooper pairs to form. The theory's predictive power and its ability to describe a wide array of conventional superconductors earned its creators the Nobel Prize in 1972. Yet, as comprehensive as Bardeen-Cooper-Schrieffer theory is, it does not encompass every superconductor known to science. In recent decades, researchers have encountered materials whose superconducting behavior cannot be fully explained by the Bardeen-Cooper-Schrieffer framework. These so-called unconventional superconductors, which include the celebrated high-temperature cuprates and, more recently, nickelate compounds, challenge our understanding of electron pairing and quantum order. In these materials, the mechanism for pairing may not rely on the traditional electron-phonon interaction. Instead, alternative mechanisms, sometimes involving repulsive interactions or entirely different quantum processes, may be at work. One model proposed for unconventional superconductivity involves the hardcore Bose-Hubbard model. Here, the electrons or their paired analogs are subject to strong repulsive interactions, and their behavior is described in terms of bosons on a lattice. In the strong coupling limit, this model can reproduce certain aspects of the unconventional superconducting state, such as the emergence of superconductivity despite the dominance of repulsive interactions. Mathematical frameworks continue to be developed to capture the full richness of these systems, but a comprehensive, universally accepted theory remains elusive. What unites all superconductors, whether conventional or unconventional, is the formation of pairs that lock their mutual quantum phases, creating a single, coherent quantum state. This macroscopic coherence is what allows electrical current to flow without resistance and magnetic fields to be expelled or manipulated in novel ways. The exact nature of the pairing, the symmetry, the interaction, the energy scales involved differs from one material to another and defines the boundaries of our current theoretical models. Critical temperature, or T sub C, remains central to both research and application. It defines the threshold below which superconductivity emerges and above which the material reverts to its normal resistive state. For most conventional, Bardeen-Cooper-Schrieffer described superconductors, T sub C is quite low, typically below 30 Kelvin. However, the discovery of superconductivity in copper-based and nickel-based compounds, so-called high-temperature superconductors, has pushed this boundary higher, though still far below room temperature. These materials, which include cuprates and more recently hydrogen-rich compounds like hydrogen-3 sulfur and lanthanum, hydrogen-10, have inspired hope that room-temperature superconductivity might one day be realized. In these systems, the nature of the superconducting gap, the interval and energy that separates the superconducting state from excited states, remains a key focus of research as it holds clues to the underlying mechanisms at work. Magnetic fields and current also play a decisive role in shaping the practical limits of superconductivity. Every superconductor has a critical magnetic field, the maximum strength it can endure before the superconducting state is destroyed. For Type 1 materials, this is a single, well-defined threshold. For Type 2 materials, as previously described, two critical fields define the boundaries of the superconducting, mixed, and normal states. Exceeding these limits, either by increasing the magnetic field or by raising the temperature, forces the material out of the superconducting phase. The critical field is closely related to the critical current, which is the maximum electrical current the material can carry while remaining superconducting. As current increases, it generates its own magnetic field, and if this field exceeds the material's critical field, superconductivity collapses. This interplay sets a hard limit on the performance of superconducting wires and devices, and it must be carefully managed in all practical applications. Intriguingly, research has shown that under certain conditions, such as the application of intense magnetic fields, the critical temperature itself can be elevated in some materials. This counterintuitive effect hints at deeper complexities in the quantum mechanics of superconductivity and opens new avenues for both fundamental research and potential technological breakthroughs. The search for new superconductors with higher critical temperatures and more robust magnetic properties is ongoing. Recent advances include the stabilization of nickelate superconductors at room pressure, which has unlocked opportunities for further study and potential practical use. Likewise, the observation of unconventional superconductivity in systems like magic-angle twisted trilayer graphene has provided compelling evidence that entirely new forms of superconductivity are possible, even at relatively high temperatures. Despite these advances, significant gaps in our understanding remain. While BCS theory elegantly explains many aspects of conventional superconductivity, it falls short in describing the full range of behaviors observed in unconventional and high-temperature materials. The precise mechanisms that allow for superconductivity in these complex compounds, the interplay of lattice structure, electronic correlations, and magnetic effects all remain active areas of investigation. What is clear, however, is that superconductivity is not a phenomenon confined to a narrow band of pure metals or specific crystal structures. It is a broad, evolving field encompassing a wide range of materials and mechanisms. The interplay between magnetic fields, current, and temperature defines the practical boundaries, while the quantum mechanics of electron pairing and collective behavior define the theoretical ones. As our exploration of superconductors continues, each new discovery, whether a novel material, a higher critical temperature, or a deeper theoretical insight, adds another layer to our understanding. The dream of practical, room-temperature superconductors remains tantalizingly out of reach, but the progress made thus far suggests that nature's secrets may yet be unlocked. The journey through the types and mechanisms of superconductors is far from over, and the next breakthrough may well come from the most unexpected quarter. Imagine a world where electricity flows endlessly, never dissipating as heat, never lost to the inefficiencies that have challenged engineers and scientists for more than a century. This dream, while not yet fully realized, comes closer to reality each year thanks to the remarkable properties of superconductors. Their applications, both established and emerging, are steadily transforming industries and reshaping what is possible in medicine, energy, transportation, and beyond. Superconductors first made their mark in technology through their powerful magnetic fields. When cooled below their critical temperature, these materials exhibit not only zero resistance, but also the ability to sustain incredibly strong magnetic fields without energy loss. This unique property underpins some of the most familiar and life-changing uses of superconductivity. In hospitals around the world, magnetic resonance imaging, or MRI, has become an essential tool for non-invasive medical diagnostics. At the heart of every MRI machine is a superconducting magnet, generating precise, stable fields that allow physicians to peer inside the human body, detecting tumors, injuries, and countless other conditions with stunning clarity. In this way, superconductors have already revolutionized healthcare. But the reach of superconductors extends far beyond hospitals. In laboratories probing the fundamental nature of matter, superconducting magnets drive the world's most powerful particle accelerators. These machines, found at major physics laboratories, steer and focus beams of subatomic particles, allowing scientists to uncover the building blocks of the universe. The same principle enables the mighty magnetic fields needed for experimental fusion reactors, where researchers hope to one day harness the power of the stars for clean, limitless energy on Earth. Superconductors, with their unrivaled ability to channel and confine magnetic fields, are a key ingredient in these ambitious scientific endeavors. The power grid, often invisible yet utterly crucial to modern life, stands on the verge of transformation through superconductivity. Traditionally, a significant portion of electricity is lost as it travels across continents and cities, dissipating as heat in the resistive wires woven through our infrastructure. Superconducting cables, however, offer the prospect of transmitting vast amounts of power with zero loss. Early prototypes have already demonstrated the ability to carry currents many times greater than conventional copper wires, with no resistance to sap their strength. This promises not just a leap in efficiency, but also the potential to reimagine the very architecture of the grid, enabling long-distance power transmission, integrating renewable energy sources, and reducing the need for bulky and expensive substations. Electric power is not the only field ripe for change. In transportation, superconductors make possible one of the most futuristic forms of travel, magnetic levitation, or maglev, trains. By exploiting the quantum levitation and pinning effects unique to superconductors, these trains float above their tracks, free from friction, and glide at extraordinary speeds. Already, maglev trains operate in select cities, offering smoother, quieter, and faster travel compared to traditional rail. The potential for expansion remains significant, with ongoing developments in high-temperature superconductors promising to reduce the costs and complexities of such systems, perhaps one day making frictionless rail travel a common experience. Beyond these headline-grabbing applications, superconductors have quietly found their way into a host of specialized roles. In scientific instrumentation, they enable the most sensitive detectors of magnetic fields ever devised. Devices known as superconducting quantum interference devices, or SQUIDs, can pick up magnetic signals so faint they are effectively undetectable by any other means. This sensitivity makes superconducting quantum interference devices invaluable in fields as diverse as brain imaging, where they map the faint neural currents in the human head, and radio astronomy, where they help detect the whispers of cosmic phenomena across the universe. Superconductors are also at work in advanced electronics. Josephson junctions, tiny sandwiches of superconducting material separated by a thin insulating layer, form the basis of ultra-fast, ultra-sensitive digital circuits. These devices are the building blocks of certain experimental computers and are central to the development of quantum computing. In sensing and measurement, superconductive tunnel junctions enable radio astronomy sensors with unprecedented precision, unlocking new views of the cosmos. The list of current and emerging uses continues to grow. Superconducting fault. Current limiters act as circuit breakers on steroids, able to instantaneously detect and interrupt dangerous surges in power lines, protecting equipment and improving the resilience of the grid. Superconducting electric motors and generators promise compact, lightweight designs with unmatched efficiency, potentially revolutionizing everything from industrial machinery to the propulsion systems of ships and airplanes. Yet for all these achievements and promises, the journey of superconductors from the laboratory to daily life has not been without challenges. The materials themselves are often expensive and difficult to fabricate, especially in the form of long, flexible wires needed for power applications. Maintaining the low temperatures required for superconductivity, especially for older, so-called low-temperature superconductors, can be energy-intensive, typically requiring liquid helium or complex refrigeration systems. Even with the discovery of high-temperature superconductors, which can operate at the more manageable temperatures of liquid nitrogen, practical implementation still demands careful engineering and infrastructure. Another subtle but significant hurdle arises from the quantum nature of superconductors. In Type II superconductors, commonly used in high-field applications, magnetic fields can penetrate the material in the form of vortices. The movement of these vortices, if not controlled, introduces unwanted energy dissipation. This effect, known as vortex motion, can disrupt the very lossless state that superconductors are prized for. Researchers have found that introducing defects into the material, carefully engineered imperfections, can help pin these vortices in place, reducing losses and preserving the superconducting state even under demanding conditions. Despite these obstacles, the technological momentum behind superconductors is undeniable. Government agencies, such as the Department of Energy, are actively developing and testing superconducting components for the electric grid, aiming to create more reliable and efficient infrastructure. High-temperature superconductors have already begun to transition from laboratory curiosities to components in real-world power transmission systems, hinting at a future where zero-loss cables, efficient transformers, and rapid-response fault limiters become routine elements of our electrical landscape. As the field advances, the possibilities only expand. The integration of superconductors with renewable energy sources stands out as a particularly promising avenue. By enabling lossless transmission and storage of electricity, superconductors could help overcome one of the major hurdles facing wind and solar power: how to move energy from where it is generated to where it is needed, efficiently and reliably. Superconducting magnetic energy storage systems, for instance, could store vast amounts of energy in circulating currents, ready to be released on demand without the drawbacks of chemical batteries. Looking even further ahead, the impact of superconductivity on quantum computing looms large. Superconducting circuits are one of the leading architectures for building quantum bits, or qubits. These systems rely on the ability of superconductors to maintain coherent quantum states for extended periods, a task that becomes easier as materials and cooling methods improve. Should researchers succeed in developing superconductors that operate at or near room temperature, the stability and performance of quantum computers could see dramatic gains, propelling this revolutionary technology into practical, widespread use. The quest for room temperature superconductivity remains the holy grail of the field. Recent years have witnessed remarkable progress, with new theory-driven methods devised to predict materials that might harbor superconductivity at ever higher temperatures. In some cases, researchers have stumbled upon entirely new superconducting states by accident, a testament to the unpredictable and exploratory nature of this science. Notably, studies have shown that under the right conditions, such as applying pressure to certain materials, unexpected electronic behaviors can emerge, suggesting new strategies for achieving superconductivity without extreme cooling. The potential benefits of such a breakthrough are almost impossible to overstate. If superconductors could operate at room temperature and ordinary pressures, the need for costly and cumbersome cooling equipment would disappear. Power grids could be rewired for lossless transmission on a global scale. Transportation, from magnetic levitation trains to electric vehicles, could be revolutionized by lighter, more efficient motors. Computing would be transformed, unlocking the next generation of both classical and quantum devices. Even healthcare would see further advances, with more accessible and powerful imaging technologies. There are, of course, formidable barriers to overcome. The fabrication of superconducting wires that can carry high currents under realistic conditions, exposed to strong magnetic fields, mechanical stress, and temperature variations, remains a significant technical challenge. The cost of raw materials and the complexity of producing them at scale are persistent issues, especially for the most promising high-temperature compounds. Ensuring the long-term stability and reliability of superconducting devices in everyday environments is another crucial hurdle on the path to widespread adoption. Nevertheless, the trajectory of progress is unmistakable. Superconductors are no longer confined to the pages of physics textbooks or the isolated halls of research laboratories. They are steadily weaving themselves into the fabric of modern technology and daily life. From the silent revolution in medical imaging to the bold frontiers of quantum computing and sustainable energy, their influence is growing. The road ahead is both challenging and exhilarating. Each advance in material science, each clever solution to the practical problems of cooling, fabrication, and stability brings us closer to a world where the magic of superconductivity becomes commonplace. As researchers probe new compounds, refine their understanding of quantum mechanisms, and engineer ever more capable devices, the promise of superconductors continues to inspire. In the decades to come, their impact may well rival that of electricity itself, reshaping the way we live, move, heal, and understand the universe.